Hello, everyone, and welcome to week 24 of Qubit by Qubit's Intro to Quantum Computing course. This is the last lab. So we'll be talking a little bit about near-term quantum algorithms. And there's also a focus in this lab really on showing you a little bit by example, as much as we can in the next hour or so, how you might actually go and investigate new quantum algorithms and learn new things on your own. So we are going to talk a little bit about some of these near-term quantum algorithms, but toward the later half of the lab, we are also going to dive into some code that you have not seen before. I have only looked at for about 5 minutes, and we're going to work together and see how one might go through some code and figure out how it works. So there'll be one part that's a little bit more like a regular lab, and then the later part is a little bit more exploratory, should be much more open-ended. And yeah, I hope it'll be fun because this is it. After this, we don't have any other labs. We did our review last week. Hopefully this will be a good chance to sort of jumpstart, I guess, all of you if you want to keep looking into quantum computing and leave you with a good impression as you come away from this course. So let's go ahead and get started. Pretty usual agenda. We have our announcements as always, followed by the Canvas attendance quiz, and then we will get into the pre-lab Zoom feedback and the lab content. Before I jump into announcements, I just wanted to cover off a few things for me personally. Last week, I said I would check in on course resources. So what's going to happen to the videos, what's going to happen to Canvas and Piazza and all that stuff. You should have received an email that clarifies exactly what's going on with all of that. The summary for the YouTube videos, by the way, which I know was an important piece for some people in this lab, is that they will stay online unlisted, which means as long as you hold on to those links, you'll still be able to access them, assuming that we don't see people abusing them, right? These are, at the end of the day, proprietary, private materials. You're allowed to use them for personal use. But as long as people, stick within those bounds, we will be keeping them up on YouTube. I'll open up the chat here as well if anybody has questions on that kind of thing. Hopefully I will be a little bit better briefed this week to answer some of those. Okay, thank you. I'll miss this too. I've had a lot of fun this year. Okay, so a couple of announcements then. The last course activity, generally speaking, is going to be a panel discussion on Sunday, May the 2nd at 2 p.m. Eastern time. So this will be, I guess you could kind of think of it as like the last lecture, but it's going to be a panel discussion. It'll feature several experts in the field, including all these people from our board of directors. Scott Aronson, Clarice, Will Oliver, and Spiros are all going to be there. They are all behemoths in the quantum industry, so I would highly recommend that you check this out if you can. And definitely check it out live if you can as well, just because they will be taking questions. I don't know exactly for how long, but this is a pretty awesome opportunity to get to ask these people some of your questions if you have them. Okay, and then I also introduced something last week called Schrodinger's Chat. I don't know if that's a typo here, but anyway, this will be streaming on Twitch at twitch.tv/qubitbyqubit. The link is right here. Over the summer, the first stream is scheduled for Saturday, May 22nd at 10 a.m. Eastern. So we will be taking a little bit of a break from the course ourselves before jumping in and offering this stream over the summer. I don't know exactly what Akshay has planned for this, but definitely stay tuned and write this down on your calendar if it sounds like something you're interested in. Okay, those are all the announcements I had. So let me just see in the chat here. I don't think there's any problems. Okay, cool. Yeah, if you have questions about course material remaining available, do check out that email. I think it's also there as a post, or sorry, an announcement on Canvas. So you can check it out there. All right, Canvas attendance quiz. We are lab number 1. As always, the attendance quiz passcode is 4869 this week. And this week's question is giving your TAs some feedback. So there's 3 statements here, and the quiz asks you to indicate your level of agreement with these statements. So your TA helped make the course a good experience. helped make you feel like you belong in the field of quantum computing? And then do you see your TA as a role model? I feel slightly awkward reading these out loud, but go ahead and answer these. Please do them honestly. I don't plan on looking at them, so just share your honest opinion. It's useful for our course admin to know how you all see your TAs and how that sort of factored into your course experience. Somebody asks, where's the link for summer quantum lectures? So I believe all of the summer programming and stuff, I'm not very familiar with it, but it should all be available at qubitbyqubit.org. So I would check there as a first resource. Okay, so I saw somebody in the, oh yeah, so a few people are saying on Canvas it's locked or they can't access this quiz. Anybody else experiencing that, or can anybody access the quiz successfully? Oh, okay. Okay. I'm not sure then. If you are having any problems accessing the quiz, you can email student@qubit.by-qubit. Right? That's the generic helpline with any questions. Okay, let's see. Somebody also asked another question about future courses. Will the next course be an advanced version of this? As far as I'm aware, we are not planning on offering sort of a second level to this course. Some of the reasoning that I'm aware of is just that there are already resources out there, such as the Qiskit textbook, that sort of take you that next step. This course has been a good foundational introduction to quantum computing. But from here, we hope that you have the skills necessary to go on and start learning things on your own. So as far as I'm aware, that's not in the cards for next year, but there are a couple of things that we've mentioned, a couple of ways we've mentioned to stay involved and stay connected if you want. Okay, awesome. So last piece before we get into the lab itself is to do our pre-lab Zoom poll, which in fact, I think is our only Zoom poll today, because we'll be having a more interactive session. So lecture this week talked about near-term quantum algorithms and specifically talked about something called QAOA, the quantum approximate optimization algorithm, which for obvious reasons, we always just call QAOA. Okay, so it looks like people are perhaps a little bit shakier on their understanding of this week than previous weeks. That is okay. And I think this week sort of falls into a category of weeks that we've seen before, where the point is not for you to understand all of the nitty-gritty details, right? If you wanted to understand the details, you could spend a whole bunch of time reading through the docs and reading through code and stuff and teach yourself everything. We just want to make sure that you get the high-level ideas so that you could, for example, explain to someone else how these algorithms work at a high level. So that's what I'm hoping to get across in the lab here today. And then, of course, when we go and look at the code itself, that'll be in a little bit more detail. But as you'll see, even in the span of one lab session, I won't be able to explain how every single line of code works. It's still going to be a little bit higher level. Awesome. All right, so I'll go ahead and share that for interest. There we go. And let's go ahead and talk about the agenda for today, or the learning goals, I guess, the lab agenda. So there's generally going to be two parts. The first one is on the slides, understanding near-term quantum algorithms. So we will specifically, again, be talking about QAOA as sort of the main subject of our discussion. And then we'll talk a little bit about a particular case study, which is a problem called portfolio optimization. So I think this is exciting because this is the first time we've sort of linked what we've learned with quantum computing into a real world problem, right? I'll explain what portfolio optimization is in a moment, but suffice it to say, it is a real world problem. It has real world consequences, and real world companies would be interested in this algorithm. And we'll show you how you can do that with QAOA. Once we've gone through some of the theory on the slides, we will then go into the code itself. And so part of the point of that is to strengthen your understanding of QAOA and the portfolio optimization problem. But part of it as well is for me to try and walk you through the discovery and exploration process. If someone throws a brand new Jupyter notebook at you that doesn't have very much instruction or commenting like many of the lab ones did, how do you go about figuring it out, right? What things do you look for? How can you try and make sense of what's going on? Because oftentimes, especially in quantum computing nowadays, the way that a lot of information is shared is it'll just be some notebook that someone wrote. And oftentimes people are in a rush, they don't leave a lot of comments. And so you need to just figure out the code yourself. And so that's what we'll be doing a bit of toward the end. Okay. So let's talk a little bit about QAOA and a little bit about how we're going to approach these Jupyter notebooks. So the first slide here is a little bit of a joke, I guess. Usually when you are programming in the real world, you'll be pulling together pieces from a whole bunch of different sources, right? So in this picture here, we see all these different things. You might have heard of them, right? Stack Overflow is a really popular question and answer site for programmers. You might pull some code from YouTube tutorials, from the docs, from some other random code on GitHub, et cetera, and you put it together into like some interesting combination of all of those different code sources. So this is sort of how programming works in the real world. You'll be able to find some source material, you'll be able to find some code that people have already written, but chances are it won't do exactly what you want, right? And so you have to sort of go and explore all these different sources, pull together pieces that you need to create something that will do what you want. So today we're going to be looking at a pre-written implementation of QAOA. So like I said, someone throws a random Jupyter notebook at you and you need to figure out how it works. This Jupyter notebook, just like real world code, has probably been constructed by throwing together a whole bunch of different pieces. And so some of it might not look as cohesive or as, as much like a single piece as you might be used to. All right, well, let's first talk a little bit about the theory of QAOA, though, before we get into this specific algorithm. The reason for QAOA and this general category of near-term algorithms, which is the title of this lab, you've probably heard it before, the reason for this is the following. If we look at the status of quantum computers over the next, current all the way up to the next couple of years, we are currently at around 65 noisy qubits. So what does this mean? 65 qubits, you know what that means. There's 65 qubits that you can play with. Noisy means that they have lots of errors, right? So last week, I think, or 2 weeks ago, we talked about errors in quantum computers. Today's quantum computers have quite a bit of error, as we've seen by running algorithms on real quantum computers. We saw like 10% error rates, right? Which is generally quite high. IBM has just released plans for a 1,000 noisy qubit quantum computer by 2023. So in the span of roughly the next 2 years, we expect to see the number of qubits grow quite a bit, but these qubits will still be noisy. So they'll probably be, at best, just as high of an error rate as what we see right now. Possibly they'll have an even higher error rate, right? There might be some of that trade-off we talked about where you get more qubits, but you also get a worse error rate. Now, to put that in perspective for some of the other algorithms you might have heard of or seen, what you need for something like Shor's algorithm or Grover's algorithm, which are two very powerful exponential speedup algorithm or polynomial or exponential speedup algorithms, you need somewhere on the order of 10,000 error-free qubits to run these on real-world problems, right? So when we ran Grover's search, we ran it with, I think, 2 qubits, right? We had 4 things to search over and we needed 2 qubits for that. Of course, you could do that on today's quantum computers just fine, but realistically, no real world problem is going to have you search through 4 elements. You're going to have to search through many more than that. And so if you want to tackle a problem on the scale of something in the real world that would be useful, you would need somewhere on the order of 10,000 error-free qubits. So there's a couple of things to point out here. Number one, 10,000 is another order of magnitude larger than 1,000. So that is significant. We would need more development to get that to happen. But probably the more important point here is the distinction between noisy and error-free qubits. And this is probably what's going to hamper quantum computing development quite a bit more in the next few years, is not necessarily the number of qubits, but the quality of those qubits, right? When we talked about Shor's and Grover's algorithms, or I guess we talked mainly about Grover's, we didn't consider error at all. Right? We didn't think about how error might affect our search. Would the algorithm remain useful even if there were errors? And the answer for Grover search turns out to be no, not really. If you have significant errors in your machine, this algorithm becomes useless really fast. And so in order to do it properly, you would need error-free or close to error-free qubits. And we talked briefly about something called error correction, right? So that would probably be how we do this in the near term. We use noisy qubits to construct error-free qubits. And error correction schemes that I'm aware of generally use somewhere on the order of 10 times the number of noisy qubits to create a error-free qubit. So again, using very, very rough numbers here, you might need 100,000 noisy qubits to create 10,000 error-free qubits to finally run Shor's or Grover's algorithms. So if you needed somewhere on the order of 100,000 noisy qubits, we're still quite a ways away from that. Now, I've blabbered about this quite a bit, but just to return to the original question, why we're talking about near-term algorithms, it's because of this discrepancy, right? A lot of the algorithms that people think about when they think quantum computing are just not possible on today's hardware, and they won't be possible on actual quantum computers for probably many more years. And so researchers have turned their attention to, okay, we have these, 1,000 noisy qubit quantum computers. What could we do with them, right? Can we still make them useful in some way to sort of fill this interim gap where we're building quantum computers, but they're not quite good enough yet to run something like Shor's or Grover's algorithm? And that's what near-term algorithms are. That's why they're called near-term algorithms. They're algorithms that are specifically designed for computers that have a large number of qubits, but whose qubits are relatively noisy. Okay, let me just quickly address some of the questions in the chat. Yeah, so somebody asks, what if you had something like 100,000 qubits, 90,000 were noisy, but 10,000 were error-free? Would that still work for Shor's or Grover's? Yes. If you just had that minimum 10,000 error-free qubits, you could run it. The issue is that we don't have anything on that scale. Somebody asks, okay, so a few questions about physical and logical qubits. So that's something else I should mention, by the way. Noisy qubits are sometimes also called physical qubits because they include all of these physical imperfections inherent in a real-world device. Error-free qubits are often called logical qubits. And I guess there's a few ways you can remember this. One would be that error-free qubits behave logically, right? We know how they behave. We know exactly how to model it with mathematics. But the other reason is that logical bits is another term that's used for bits in classical computing. These are the qubits that behave as we expect. So somebody's question here says, isn't Shor's error correction code, so not to be confused with Shor's algorithm, Shor also came up with an error correcting code. It needs 9 physical qubits for 1 logical qubit. Exactly. Yes. And so if you use Shor's error correction code, then you would need, for these 10,000 error-free qubits, you would need 90,000 noisy qubits. There are other error correcting codes that deal with more errors, though. So Shor's error correction does not necessarily deal with every type of error out there. It deals with a good portion of them, 2 very common types of errors. But it's possible, and I don't necessarily know the details on this, it's possible that you would need to protect against other kinds of errors to run something like Shor's or Grover's algorithm. But that's why I said somewhere in that realm of 9 to 10 times would be a rough approximation of how many qubits you would need. Okay, so actually, this is also a really good question. Somebody asks about 10 parallel quantum computers, right? So if you had 10 quantum computers, say with 1,000 error-free qubits each, would that still be enough to run Shor's or Grover's algorithm? And the answer here is likely not, which is a little bit interesting because in classical computers, of course, we know you can parallelize things quite easily. The thing with quantum computers, though, is that when we talk about having sort of 10,000 error-free qubits, we're talking about 10,000 qubits that could all be put in superpositions with each other. They could all be entangled with each other. They could all interfere with each other, right? So those 3 key quantum properties could be utilized between any of these 10,000 qubits. If you had 10 separate quantum computers, each with 1,000 error-free qubits, maybe you could do entanglement within each computer, but you could not, for example, entangle a qubit between the first and seventh computer. And in some cases, that would break your ability to do Shor's algorithm, for example. Okay, so I think I'm gonna pause questions there just so I can keep going with the slides. But these are all great questions, and I will, as always, come back to them toward the end of the lab. Okay, so going back to this, why we need near-term algorithms, what quantum computers look like nowadays. Of course, we would like quantum computers to be able to do Shor's algorithm, Grover's algorithm, etc., but the technology just isn't there yet. So, quantum computers, maybe by the year 2050, will be like these super powerful devices that can solve all these crazy problems. Again, we're just not there yet. And so this is the question that near-term quantum researchers pose to themselves. What can we do with the quantum computers we have right now, or will have within the next 5 years, that might still be useful? So the first thing that people, or I don't know if it was the first necessarily, but one very popular line of research is to think about using quantum computers in tandem with classical computers. Right? So in this case, it might be like the classical computer is still Batman, but the quantum computer comes in as a sort of sidekick to do some portions of the problem. So the idea here would be you offload only the part of the problem that is extremely difficult for a classical computer to the quantum computer. The classical computer still does the majority of the work. These are what we call hybrid algorithms. So hybrid just because they're using both a quantum and a classical part. And so when people discuss hybrid algorithms, you'll often hear them discuss the classical algorithm or the quantum algorithm or the classical part and the quantum part. That's the kind of language that is typically used here. And in fact, QAOA, the algorithm we're going to look at, is one example of a hybrid algorithm. So as we'll see in a moment, there is a part of the algorithm that runs on a classical computer. It feeds over to the quantum computer does some stuff, then it passes back to the classical, and so on and so on. And so it's sort of a cycle. To illustrate how QAOA works, we're going to play a little bit of a game. So the slide here says that we can guess your TA's age. I think it might be a little bit easy to guess my age. I don't know. Maybe not. But instead, I'm going to say, why don't we go with guess my height? Because that might be a little bit harder. So the way that this is going to work, and I'll say height in centimeters, right? I'll get some people just in the chat to throw out some guesses, right? And for each of those guesses, I will tell you if you should go higher or lower than that particular guess, okay? So just give me one moment here. Okay, I'll look at the first one that I'm seeing here. Somebody says 172. That is the first guess. And I will say I am taller than 172 centimeters. You should go higher. Okay, 180 is the next one I see. 180 centimeters, you should still go higher. Okay, I see 185. Okay, 185 centimeters, you have to go lower from there. I'm not that tall. Okay, some people are saying 183. 183 centimeters, that's correct. That's how tall I am. Cool, so thank you for 210. Oh my gosh. Okay, so yeah, this is a perfectly valid way of guessing an answer. And in fact, this is pretty much how QAOA works, right? So we're going to have the quantum computer essentially make some guesses. And the classical computer, the thing that's easy or relatively easy for a classical computer to do is to tell you whether your guess is too high or too low, even though the classical computer itself doesn't really know what the answer is. Okay. So, oops, I was writing over my slide here. I probably shouldn't have done that. But in this analogy, like I said, you're the quantum computer. So the quantum computer is the one who's throwing out guesses. And based on my feedback, you update your guesses to solve the problem. Again, in this analogy, I would be the classical computer. So it turns out that the piece of this problem that's easy for the classical computer is the part where I just tell you, is your guess too high or too low? Now, I grant this analogy is not the most perfect in the world because I obviously know the answer to the problem. In an actual QAOA problem, the classical computer does not know the answer. It just knows how to judge whether the answer, the proposed solution from the quantum computer is too high or too low. And finally here, just a point, I guess, optimization problems generally are an exciting application of near-term quantum algorithms. So near-term quantum algorithms are often fall into this hybrid category, and QAOA is one of the most popular hybrid algorithms. Okay, so that was a great example actually of this particular game because you started off a little bit low, you started off and then you went higher again, and then you kind of converge in on the correct answer. And so if this is my age or height, you get the point. Your guesses kind of look like this, right? You might have started a little bit too low, and then you might have overshot, and then you would know that, okay, our next guess has to be somewhere in this range, right? So you're no longer going to guess anything under this point. So you'll guess something a little bit closer to the correct answer. And then as we keep going, you keep getting closer and closer to the correct answer until on your last guess, you guess it correctly. So we'll see when we get to the notebook a graph that looks almost exactly like this, because this is pretty much how a QAOA algorithm works. You'll see some kind of crazy guesses at the beginning, but over time, they're going to converge to the correct answer. So hopefully this idea of sort of converging to the solution based on feedback to your guesses makes sense, because that's really the high level idea of how QAOA works. Okay, let's take one more look at hybrid algorithms. This is just another way of drawing essentially what I have been saying. So you're going to start off with some initial guess, right? You feed that into your quantum computer. Your quantum computer does some kind of measurement. You feed that measurement into the classical computer, and the classical computer spits out some new guess, feeds it into the quantum computer, spits out measurement results, and this cycle just keeps going. And usually you'll have some kind of threshold where once the guess is close enough or good enough, then you'll stop this cycle and spit out the solution. So you can see that there's this main component here where we're going in a cycle from quantum to classical, back and forth again until you choose to stop. Okay, that is pretty much all I have to say on hybrid algorithms and QAOA. I think those are the high level ideas. So now I'm going to introduce the case study, the specific problem that we're looking at for this particular lab, which is portfolio optimization. Like I said, I am excited for this just because this is the first kind of real world connection to quantum computing. All right, let's imagine the following scenario. You are a stock trader and you would like to see what the best selection of stocks would have been for a given day. So note that this is not quite, trying to predict the stock market. That would be a different kind of problem. This is if you have all of the data for all of these different stocks, which ones should you have picked in hindsight, right? So it might sound like this is an easy problem, and it is a bit of an easy problem for a small number of stocks. But as soon as you start getting to any sizable number of stocks in your portfolio, this becomes quite difficult. So for example, if we had a portfolio size of 20 stocks, right? We wanted to invest in 20 stocks. There are 3,300 listed stocks on the NASDAQ, just as one example. So NASDAQ is if you don't know this term, it is a popular American exchange where you can buy and sell stocks. And so my question is, roughly speaking, how many different portfolios would you need to consider? If you wanted to find out the optimal portfolio, how many different portfolios are there? Right? So give this a little bit of thought on your own. I don't have a Zoom poll for this or anything, primarily because doing this kind of problem is not actually part of this course, just kind of a fun mental exercise. Right. Okay. So somebody here uses the choose function. We've seen this come up a couple of times before, but again, no worries if you're not familiar with this. We would write this as what's called a binomial coefficient. 3,300. Choose is how you read this, 20. Right? And again, no worries if you don't know this, but I will just tell you right now, This is somewhere on the order of, if I did my calculations correctly, 10 to the 20. So that's pretty big, right? That is 1 followed by 20 zeros, basically. So a huge number, trillion, 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 something like that, right? And the sheer number of portfolios, that you have to go through is so large that this problem becomes difficult, right? If I give you one particular portfolio, or maybe let's say if I give you two portfolios and I ask you which is better, that's a pretty easy problem, right? But if I give you all these possible portfolios and I ask you which is best, that becomes very difficult very quickly. Okay, somebody's asking, how did you get the 10 to the 20? Did you use a calculator? I actually did not calculate this. This is just in my notes that it's about this value. You wouldn't be able to plug this into a calculator as far as I'm aware. But there are some, well, actually, this is one thing that you would know. So this combinatorial function, this binomial coefficient, right? If you have generally n choose k, there is a big O notation expression for how this grows, right? So even if you don't calculate the exact number, there is, and I don't know exactly what it is, you could look this up online, but you could say like the asymptotic growth of the binomial coefficient, and that would tell you some expression for roughly how fast this grows. That's probably how this was derived, but I'm not exactly sure. Yeah, and as somebody points out, just to underline this point, prediction of the stock market is not what we're after here. Prediction of the stock market is quite difficult and an entirely separate problem. Oh, wow. Somebody says 10 to the 50. Okay. Well, I guess I was a bit off. Anyway, the point here is just that it's a huge number, right? And this number means that it is almost impossible to just go through and check every single one of these different combinations using a classical computer, unless you had some kind of like supercomputer, right? Okay. So as the point says here, classical computers can do this today, this size of problem, barely. You would need a very powerful computer and you would need quite a lot of time to let it run. But as the number of choices gets bigger, so for example, if you went from 20 to say 50 stocks, the optimal solution gets much harder to find. Or if you had more stocks listed on the exchange, say that there's now 5,000 on the exchange, this just becomes way harder very quickly. And so QAOA is going to let us do this slightly more efficiently. All right, when we look at our notebook, we're going to have a slightly simplified version of this problem, but not too much. It's still the same idea. Instead of 20, we're going to take 5 stocks to choose from, right? So again, we're still going to have the full size of the NASDAQ, all 3,300 of them, but we're only going to be picking 5. And that's going to make it so that we can find a solution with a classical computer relatively fast, just so we can check our answer. Oh, I'm sorry. The total number of stocks here, I messed up. The total number of stocks here is 5, and you're holding 2 stocks in your portfolio. So again, this is going to be a simplification of the problem just so we can compute it with a classical computer. And again, so this case, there's only 5 choose 2 different portfolios to consider. So much easier, right? That was my bad for misspeaking earlier. Okay, so given this, the problem statement is still the same. Our goal is to maximize our returns given the budget. So in this case, by the way, budget just means how many assets you can hold. So it's 2. And the amount of risk you're willing to take. So we'll have some number to quantify risk in this case as well. My next question then is, what information do you need to pick these stocks, right? By the way I've set up this problem, hopefully a few things start coming to mind, right? A few numbers that you might want to start picking these stocks. One obvious one, if we're trying to maximize your returns, you probably need to know what the returns of each individual stock is, or what the return of each individual stock is, right? That makes sense. And we're also trying to take into account the amount of risk we're willing to take. So we also need some measure of risk for each of these stocks. So looking at the historical performance of the stock, like I said, we know the historical data in this version of the problem. There's 2 things we want. We want the average return of the stock, right? So this is how much do we expect to make from a particular stock. And then the second one is the variance in that return. So variance is a statistical term. It's related to standard deviation, and it basically reflects how much risk is involved in that particular choice, right? So you could have, just to illustrate, you could have two stocks whose returns look like this. One maybe goes crazy, but ends up being fairly high, and so it has a decently high average. And the other one is much smaller fluctuations and slowly trends up, right? This one would have lower variance. That's all that means. Okay. So let's talk a little bit about the process of optimization we'll be using. Step one is going to be to create what we call a cost function. So if you haven't heard this term before, it's a very good term to become familiar with because it's used all over the place. You'll probably hear it again. A cost function is literally a function, right? So we'll define some, f of x, where x is a possible solution, right? So in this case, each x would be some combination of two stocks to pick because that's our budget. And this cost function is going to spit out one number that incorporates everything we care about. So it's going to incorporate the average return, it's going to incorporate the variance, and it's also going to incorporate the budget constraints and any penalties for going over budget, right? So you could also imagine a scenario where you want two stocks, but maybe you're willing to go up to three if there's significant benefit to doing so, right? A cost function could capture that. And so this single function basically incorporates everything that you want to solve in this problem. I won't go into exactly what this cost function looks like, but it's literally just some function, right? You plug in a solution, it gives you a number. And with that said, the goal, actually, before I go on to that one, the goal of the optimization process is then to minimize this cost function, right? So you could do it to minimize or to maximize, doesn't really matter. But usually you design your cost function so that a lower value means a better solution, okay? All right, then step two is going to be to convert this cost function into a quantum operator so that the classical and quantum computers can communicate. So we need our quantum computer to be able to evaluate this cost function, and so we need to convert this into a quantum operator somehow. So this is very similar to what we've seen in previous problems, where we had to sort of take our classical understanding of the problem and convert it into a quantum operator. Usually the sticking point there is that you need to make sure it's reversible, right? Remember, we talked about that with oracles. Okay, step three, pretty straightforward. You take your operator and you put it into a circuit and you measure the outcome, right? So we know how to do that. We can do it using IBM Qiskit, either on a real quantum computer or in a simulator. Then step four, so this is going into our loop. Sometimes you'll hear this called the optimization loop. Based on the measured outcome, we're going to adjust the quantum operator. So our classical computer is going to do some number crunching and give the quantum computer a slightly different operator to measure. Okay, so that's the part where we get some feedback, then we update our guess. And then we're going to repeat this. So steps 3 and 4 are the quantum classical loop, where you jump back and forth until the change in the measured outcome is below a threshold, and we conclude that the algorithm has minimized the cost function. So very much like when you were guessing my age and or guessing my height, and we sort of converged on a solution, here you'll see that we jump around a lot at the beginning, but eventually we start to hit a local minimum, right? So things are going to reduce down to some minimum value, and once the slope becomes shallow enough, we'll end our algorithm. And display the final solution. There you go. Okay, so we're almost ready to jump over to the notebook. Like I said, we're going to be looking at an implementation of QAOA for portfolio optimization at a relatively high level again. So as this point says, we'll try to make sense of what's going on in the implementation. Critically, though, we won't be able to understand everything within the lab time. As you'll see, or if you've already opened the notebook on your own, there is quite a bit going on. That's okay, though, because we're not going for perfect understanding. Like, yeah, you could rewrite this exact code given no other resources. No, we're just going for general understanding. And like this says, it would take you probably quite a while to read through every line of code. So again, the part of the point of this is to show you what the exploration and development process is when you're learning quantum algorithms yourself. You don't want to start by trying to understand every single line of code, right? You want to start by sort of trying to give yourself a higher level summary of what's going on, and then you can jump into the specifics of how the code is written. One final note here, this notebook that I'm going to show you is one possible implementation of portfolio optimization with QAOA, but this is an active research area. These implementations are literally being developed right now. So there might be more updated, better versions out there that you could find. This is just one example we're going to use to teach. Okay, so a couple of quick pointers, I guess, before we jump over to the notebook of what we call coding in the wild. This is just to say, when you have a piece of code that's not written up nicely as our wonderful teaching staff does to prepare your notebooks, how do you approach that problem? A few things. Number one, if you want to develop your own code, finding some open source code for a similar problem is often a good first step. See how other people approach it, see what previous solutions exist, don't reinvent the wheel, all that kind of stuff. Second step, which is one that we are actually going to follow today as well, is to just run the code, right? Make sure you can get the code on your computer or on your IBM Quantum Experience account or whatever, and make sure you can run it, right? You're already going to be needing to solve some problems if you cannot run the code as given. Once you know that the code runs, then you see what you can change, right? So are there any parameters in the code that we can play around with, see how it affects our answer? If you run into anything that you don't understand as you're going through the code, you can use Google or Stack Exchange or any other resources you want to try and figure out what the meaning of those particular functions or commands are. And then these last ones we're not going to follow today, but they're just generally good advice, I think, for exploring new code. The first one is to establish dependencies, right? So think about which parts of the code depend on which other parts. Often there's going to be many sort of independent pieces that each do their own part, but then they're going to come together in some way at some point to produce a final answer. And then final one that can help as well is removing fluff. So basically getting to a minimum working example. One way that you could do this, you could see this in this current example, is if you downloaded a notebook where it gave you all of that stock information, right? 3,300 stocks, trying to pick 20, it's going to take several hours to run, and you try running it and it doesn't work. You don't want to try and debug something that big. So instead, what you can do is remove some fluff, get it down to a more minimal example, like picking 2 stocks out of 5. Okay, so this is all I have before we jump over to the notebook. I'm going to pause to answer any questions that are in the chat. I know people have been chatting about stuff to do with machine learning, and you would be absolutely correct if you think this kind of sounds like machine learning. It's not well, actually it is quite similar. It's certainly inspired by machine learning. Let's say that. Someone also DM'd me asking to repeat the problem statement. Yes, so again, to underline the difference here, we're not trying to predict stock performance. We're given the performance of stocks over a period of time, and we're asking the question, which stocks should we buy at the beginning and sell at the end, right? And we're given some maximum number of stocks that we can hold. So out of the 5 stocks in our little world here, we're allowed to pick 2 of them. Which are the best 2 stocks to pick given our desires for average return and risk? Yeah, and what I mean by a high level explanation is just a explanation that doesn't get into the detail of every single line of code, but more just hopefully gets you to a point where you understand what the code is doing generally, right? You can look at each code block and figure out what it generally does, but not necessarily what every single line of code does. That's what we're going for here. Okay, so any other questions about the setup here, right? Just another quick summary. We've talked about this idea of a quantum classical optimization loop. That's really important. We'll see that in the code. And then the second key idea here is what problem we're solving. You often want to do a lot of research on the problem you're solving before you read the code, because as you'll see, there's going to be some technical jargon in the code where you sort of need to understand the problem to even have a chance of understanding the code. So our problem here is trying to select the stocks we want to buy, which are going to give us the best, average return and volatility that we're looking for. Who wrote the code? So I believe, I might be wrong on this, but I'm pretty sure this was adapted from a Qiskit example. So I think probably someone at IBM wrote the original stuff. And then I think it was Phil, who, like TA Phil, who went through and sort of cleaned up the code, brought it down to a more minimal example for us to look at. So he kind of did this last step for us already. Okay, so if there are not any more questions, why don't we hop over to the notebook? So I'll stop sharing my slides here, and I will instead go ahead and share the notebook. Okay, so hopefully everybody can see my screen here. The first thing that I'll point out is that our notebook here doesn't have any introductory text. It just starts off with a whole bunch of import statements, and we're off to the races. This is much more similar to what you might expect from some random notebook you find on the internet. Usually, people do not take the time to write, really nice, lengthy introductions that give context on what they're doing. Usually, it's more like this. Okay, so let's go ahead and get started though. I'm just going to read through this, sort of do one quick pass throughout the whole thing, following that advice to make sure that everything runs, right? So I'll go through each code block, maybe talk a little bit about them, and then I'll go back and go into a little bit more detail on some of these code blocks. So the first one here, I don't care too much about. This is just a whole bunch of import statements. You can see we're Qiskit Aqua, maybe we haven't seen that before. Qiskit Finance, again, doesn't matter if we haven't seen these before, we'll get into them later on. So I'll go ahead and run this cell. Again, once this turns into a number, we know it's done. Okay. So here we get a little bit of a warning. It's a deprecation warning. Generally speaking, warnings are not the end of the world as long as it's not an error. So you can see here it's saying Qiskit.finance has been moved to Qiskit_finance. That doesn't seem too important. Okay. So let's keep going. First step here is to pull stock data. So I'm guessing what it's doing here is fetching the actual data for the stocks, right? So again, going back to the problem that we're solving, we're not trying to predict anything. We're trying to take historical data and make decisions based on complete knowledge of what happened. So here you can see that we're selecting some stocks. So these are probably the 5 stocks that we're going to be looking at: Google, Apple, Netflix, Adobe, and IBM. We have a token here, and then we have a try except. So this is just going to try and catch any errors for us. And you can see here we're starting off at a particular time. It looks like June 1st, 2018, all the way up to December 1st, 2018. So far, hopefully this is making sense. We're pulling stock data, whatever that data is. I don't necessarily know, but we're pulling some kind of stock data for these 5 stocks between these 2 times. Cool. Okay, so I'm going to go ahead and run this. And, oh, actually, that's pretty quick. Cool. Okay, and again, I'll go back through these in a little bit more detail in a moment, but I just want to make sure that the whole notebook runs, again, following that advice. Okay, now we're going to draw the stock data, and we also draw a normalized version. Okay, so in here, if I look at this code, we have fig axes equals plt.subplots. If you've read a lot of notebooks before, you will probably recognize this as matplotlib code. But if you didn't know that, one thing that you can do is at the very top here, we see something called PLT, right? And PLT hasn't been defined anywhere else, right? We defined stocks, num assets, token, wiki, all that kind of stuff. We haven't seen PLT before. So if you ever run into a symbol that you don't recognize, one good place to start is the imports, right? So if I look around here, you might look and look and look, and eventually you'll find, oh, there's PLT. PLT is referring to matplotlib.pyplot. So indeed, that whole section of code down here where we're drawing stuff, it's just matplotlib code. I don't really care what it does because we can run it and see exactly what plots it produces. Okay, so it produces 2 plots. Here we have the yearly evolution of stock prices. You can see that our 5 stocks here are listed in different colors. You can see the dates here. I don't know if I can zoom out somehow, but anyway, you can see some of the dates listed down on the bottom, and you can see that they move around. And then we have a normalized version. So normalized here, even if you don't know what it means, you've heard the word normalized before in this course. It doesn't really relate super closely to this, but we know that our vectors had to be normalized to be valid qubits, right? And so the idea of normalization, whenever you hear that word, is just putting everything on the same scale, right? So here you can see Google, for whatever reason, the stock is worth quite a bit more than any of the other 4. If we want to put them all on the same scale, we normalize, right? So this is just plotting them between their overall minimum and their overall maximum. So now it's a lot clearer that, they all hit their minimums around the same time, right? There was this obvious dip at this particular time. Okay, cool. So now just updating my knowledge about what we've seen so far. We know that we pulled some data on these 5 stocks, and now we are plotting the data. And it seems like the data is just roughly the returns over time of these stocks. Somebody says, shouldn't the shape remain the same after the normalization step? It should. And in fact, I think it does. The only thing is that you're seeing the peaks and valleys, they're zoomed in, right? So it's kind of like if you stretched the minimum all the way down to the bottom of this plot and the maximum all the way up to the top. If you stretched and did that for every single one of these 5 stocks, then you would get something that looks like this. So for example, this valley here that we see, you can see that valley roughly here. It's not as pronounced for these stocks just because the scale is not really appropriate for the price of those stocks. Okay. Oh, phone's ringing, sorry. All right, so once we draw out these plots, the next thing we're going to do is go ahead and calculate mu and sigma. So we can see here that these are just calling some functions on wiki. And if you forget what wiki is, we can always go back to where that was defined up here. Wiki was our name for the data, right? So once we went ahead and fetched all of this data, we're saving it in wiki, and then we're getting the mean vector and getting covariance matrix. Don't really care what that means yet. So I'll just go ahead and run it. Okay. So again, like no worries if the code is not making tons of sense at this point. I'm just going through it to try and make sure we can run things. And so far, everything has been running successfully. All right, next up, setting some optimization parameters. So this is interesting. We have some hard-coded numbers here, right? So Q seems to be some measure of our risk. So we have a nice neutral 0.5 risk factor, whatever that means. And then our budget. We know what that is. That's the number of stocks we're allowed to pick, right? Okay, so these things, I don't necessarily know what this is. We're creating an operator. Okay, so this is probably important, right? Here we are creating an operator to use in our quantum circuit. And then it says here we're setting up a classical optimizer, and we get something called QAOA. So QAOA, if you don't know what this is, number one thing to do is just Google, right? So I'll just go ahead here and Google QAOA. See if anything comes up. You can see I've already poked around in this apparently in the past, but we can just pick one of these links and it'll give you some information, right? So I guess if I Command F for QAOA in here, go to that. Yeah, and so here you can see that QAOA is a derivative of Powell's implementation of this constrained optimization by linear approximations algorithm for derivative-free optimization with nonlinear inequality and equality constraints, blah, 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 with some other papers here if you want to read more about it, right? So don't need to know the details, but generally it seems it's an optimizer, right? It's going to do the classical part of our optimization. Cool. Okay. What else is interesting in here? Okay, so that's the classical part. And then we see down here some code that we are more familiar with, setting up the quantum part, right? So we're going to get error.get backend. Looks like we're going to use the state vector simulator. And then we set up this quantum instance thing, which we haven't necessarily seen before, but if you wanted to, you could look this up, see what it does. Okay, let me run that cell. Okay, and now we have two things that should again look familiar. We have a classical part and a quantum part. So the classical part is just going to be using this NumPy minimum eigensolver. Again, we don't really care what this is. It's using some built-in function of NumPy to do a classical optimization for us. So I'll go ahead and run this. And then for the QAOA solver, well, we can take a little bit more of a look at this. So we have some empty arrays here. We have this function store intermediate result, which is just going to append to those arrays. Doesn't seem too interesting yet. This seems important, right? QAOA, we're calling this QAOA function. Again, I don't know where this is coming from, so I'm going to go back up to the top and check for that. So if I look, here's Kobola, so we know where that came from. Here's QAOA. Okay, so QAOA is coming from qiskit.aqua.algorithms. I'll go ahead and Google that. So I'll just do Qiskit aqua QAOA. Pick the first link here. Okay, so this is a function that takes quite a few arguments, as you can tell. And purely judging from the length of this page, there is quite a bit to learn about how this thing works. But okay, so we're using some built-in function in Qiskit to run the quantum part of the optimizer. I can make do with that. We have this quantum instance. This actually looks like just some duplicated code, right? We saw this same quantum instance business earlier on. Very common in code that you find online, that there's some imperfections, some stuff that doesn't quite make sense. This probably isn't needed, but whatever, we won't mind too much. And then final step here, QAOA result equals QAOA.run with this quantum instance. So this seems to be the step that's doing the work for us, right? So I'll go ahead and run this. I'm expecting that this might take a little bit longer because we're running QAOA, but I tried this a little bit earlier and it didn't take too long. So I'll give it just 10 seconds or so here. Okay, and it's done. As we can see, this turned into a number. And so now we have this variable QAOA result, which hopefully we can extract some information from. All right, and now we're getting close to the end of the notebook. We have this cell here, top computed results for each solver. So we have a function being defined called find best. Some stuff in here I don't really understand. That's okay. If you kind of just get hit with a whole bunch of stuff like this, my usual strategy is just run it, see what it does, because oftentimes if you can see what it does first, you might be able to go back and make some sense of it. Okay, so this is interesting. We get some tables here. Let's see what this says. So QAOA optimal stock combination. It looks like this is some kind of answer, right? So Google and Apple, this fits our understanding of the problem, right? These are 2 stocks out of the 5 we started with. And QAOA is telling us that this is our answer. It also gives us some results here though, right? So it gives the qubits that are lit up. So in this case, it looks like it's using 5 qubits. 1 means that the stock is selected. 0 means it's not. That seems like a fairly logical way to represent things. And then we get our selection here. So which stocks are picked. Value, this might not be super clear, but usually in these optimization problems, value refers to the value of the cost function, right? So remember that cost function that incorporates everything we want about the average return and the average volatility and all that kind of stuff is captured in this value. And then we get some probabilities here. So these are all around, 10% probability, that kind of thing, 9%. And this for QAOA is basically saying you ran QAOA, you end off with some particular quantum state, And what you measure is always going to be, one particular basis state. And so it looks like our superposition, or sorry, our result was some superposition of all of these basis states, right? With roughly 10% probability each. Okay, let's see. So if I look down these values, the only thing that seems a little bit weird to me here is the best value. Remember, the cost function is something we want to minimize, right? We want the smallest value. And so it seems like the smallest value is actually down here, Netflix and Adobe, even though QAOA spit out Google and Apple with higher probability. So this might be an instance of QAOA just not finding the correct answer necessarily. There is some inherent randomness involved here. So if you ran this multiple times, you would probably see that these probabilities would change a little bit. The values would stay the same, but the probabilities might change a little bit. That's totally normal. Okay, and then down here we have a comparison with a classical optimal stock combination. So the classical one is, because this is a small problem, we can solve it exactly using a classical computer. And the exact solution, turns out, is Netflix Adobe. And it gives us the same minimum value of the cost function. Okay, so we've interpreted the results a little bit. I believe, yes, this is the final one, the cost function convergence graph for QAOA. So if I go ahead and run this, this looks like more matplotlib code, right? PLT, whatever. We go ahead and click run. We get a plot, okay? And this should look kind of similar, at least, to the plot that I drew as you were guessing my height, right? We start off with some kind of crazy random guesses, but over time, we're getting better and better and better. And you can see that the QAOA is gradually converging to whatever our optimal cost function is. So after 500 iterations, we seem to be at a pretty decently low value. And that's it. So to recap, what we've done here is we set up a simplified version of our problem where our world only has 5 stocks and we're only picking 2 of them. We ran that through a classical optimizer and the quantum optimizer, and we got, slightly different results, but at least the same optimal solution was showing up here. And if we ran it again, maybe we started playing around with the parameters a little bit, we might be able to get better results out of our QAOA function. Anyway, the whole point of this was just show it all works. This looks good. Now we can go back and start playing with it a little bit more. I know that I am at time here, so I'll say that that's the end of the required content, just to have a very high level understanding of what's going on in this code. I will throw up the post-lab Zoom feedback if you can fill that out. I'll just go ahead and relaunch that. So yeah, let me know how you feel about hybrid algorithms, QAOA, now that we have walked through a little bit of the theory and walked through a specific example. And then in the optional content, I'll spend a little bit more time going into this code in more detail, maybe exploring some other documentation pages a little bit. And then, of course, as always, I'll have time at the end for random questions. Okay, so I'll take just a 30-second break, and then we'll come back into optional content. All right, so actually before I hop into going back into this code a little bit, I'm just going to address some of the questions that have been popping up. Let's see. So somebody asks, if we increase the iterations, does the cost function go to minus infinity? This is a great question. So here you can see that we seem to have run QAOA for 500 iterations, right? So that's 500 of those quantum classical cycles, right? So it went around that loop 500 times. If we extended that, if we ran it up to like 1 million iterations, would we expect the cost function to keep getting lower? So maybe think about that for a second, right? What is the cost function representing? It's some measure of how good our selection is based on our preferences for returns and volatility. But there's only 5 stocks to choose from. There's only so many possible pairs of stocks we can pick from there. So could the cost function ever really get to minus infinity? Right? Hopefully you find there that the answer is no. The cost function has some minimum, right? One of those pairs of stocks that you can pick is going to establish the absolute lowest that your cost function can go, unless you started adding more stocks or anything. But given the definition of this problem with our 5 stocks to pick from and our budget of 2, there is a hard minimum on how low our cost function can get. Are we being graded for attendance in today's lab? I think so. It's interesting that you're not seeing it show up exactly as it usually would. I haven't been told otherwise, but I might just not have seen that particular memo. Okay, so somebody asks, what's the difference between QAOA and VQE? So this is something that I would encourage you to look into yourself, right? QAOA, the main defining feature of it is this quantum classical optimization loop, right? And so VQE, I think it's fair to say that QAOA is actually sort of like a special case of VQE. So is that always true? Okay, don't necessarily quote me on this. But QAOA and VQE are similar in their approach of sort of doing this loop between quantum and classical business. But VQE has a different purpose. It's trying to find the minimal eigenvalues of a particular operator. We won't talk more about exactly what that means, but you can think of it as an optimization problem. And conversely, you can convert an optimization problem into an eigenvalue problem. In fact, if you look at this notebook, the way that we're solving it classically is with something that's called an eigensolver, which might suggest that the classical computer is using some linear algebra to figure this out. So VQE and QAOA are certainly related. I think the biggest difference, though, would just be how you state the problem, right? Is it primarily a problem of finding eigenvalues, or is it primarily an optimization problem? Hopefully that makes some sense. If you want more detail, though, certainly go ahead and read about it. Okay, let's go to the code. Yes, absolutely. So I'll go ahead and share the results of this post-lab poll if you are interested. And all right, let's hop back to the code for a little bit. So I'm just going to go back to the very top, and there's a few things that I want to point out as sort of just interesting pieces, right? The first one that might have seemed a little bit weird the first time we were reading through this was this Wikipedia data provider. And I guess my main point here is if you wanted to start playing with this, right? If you wanted to, I guess there's not really any obvious parameters to change here. Obviously, if you wanted to see a different year, it seems pretty clear how to do that. But if you wanted to start playing around with this more, you would want to Google things, right? A lot of programming and a lot of exploration and discovery in programming is at the end of the day just Googling. So one thing that I find useful, it might be possible to just go ahead and search up. Oops. Can everybody still hear me? Yes. Okay, good. Let me just fire off a quick message on Slack because I think somebody just signed into this this Zoom account. So I want to make sure they don't start another meeting because then we'll get kicked out. Okay. Hopefully we don't get kicked out. Okay, let's go back to this. So I'm going to go ahead and try searching Wikipedia data provider. See if this gives us anything. Okay, and the first result here is Qiskit.finance, right? So this is probably what we want to be looking at. If that doesn't work, right? If you Google it and you don't get something that seems related right off the bat, one strategy that I'll often use is look at where this is imported from, right? So this Wikipedia data provider, if we go back up to the imports, you can see this is coming from Qiskit.finance.data providers. So you could Google Qiskit finance data providers, Wikipedia data provider, and that would very likely give you the correct page. So once I'm here, you can see, the various parameters it takes. You can read a little bit more about it. Please see this for instructions on use, right? So if you wanted to explore this more, you could. Okay. So let's go ahead a little bit down. I think there's not too much interesting things to see here. Matplotlib is just plotting stuff. The next, I already showed just Googling Cobala. So if you wanted to play around with some parameters on Cobala, you could possibly do that too. Okay, let's see. We'll just keep scrolling for a little bit. The part I wanted to talk about was this. So remember before, as we were sort of reading through all of this, I sort of jumped over this line, but it certainly seems like this line is pretty important, right? The whole point of this notebook is to run QAOA. This is the part where we define our QAOA and ultimately run it. So if I were looking at this code, I think it might be useful to dive into the documentation of this QAOA function a bit. So I already Googled this earlier, right? And we found this page. It would probably be worth taking some time to read through this because as you can see, when we call QAOA, we set it up with 1, 2, 3, 4 parameters, right? Up here, you can see QAOA takes way more than 4 parameters if you wanted to experiment with it, right? So some of them we've seen, like the operator, we've already used that. We're passing in our Qubit operator that we created using the finance library. Our optimizer was Cobala. Here, P defaults to 1. We seem to have passed P equals 3. Nothing in this notebook explains what P is, right? But if you read down here a little bit, you'll see under parameters, P, the integer parameter P as specified in blah, right? So if you wanted to learn about what this meant, you would go ahead and give this paper a read, right? So that would be another good function to sort of look into, read more about. Maybe increasing or decreasing this p-value would give you better or worse results, right? We don't know, but you can always give it a try. Okay, and then the final thing that I wanted to do was just play around with this a little bit, right? So first thing was to demonstrate that these results are indeed a little bit random. So if you look at this right now, our probabilities are all around 10%. I'm going to go back up here, though, and run this again. So see, the only thing that I'm a little bit, personally, I'm a bit confused about, and maybe if you read this a little bit more, you could figure it out. It seems like we're providing seeds to this. And seeds, again, if you don't know what these are, you can look up what a random number generator seed is. But that should actually fix the execution of our algorithm. It should remove all the randomness from it. Let's see if that happens, though. So our first probability was what, 0.0948? So if I go ahead and run this, yeah, okay, so this time, totally different results, right? This time, all of our probabilities are around 7%, and it actually got the correct answer. So I'm not exactly sure why that happened. Maybe I'll go ahead and run it one more time, see if this is really and truly just randomness. Wait for it to finish. And by the way, if it sounds like I don't really know what's going on in this code, it's because I don't really know what's going on in this code. So here we go. Our probabilities have gone down again, but it still found Netflix. So I'm not exactly sure what's happening here. But if you wanted to keep playing with this, I would probably suggest, running 10 trials, see what happens, but then you could start changing things, right? For example, you could change this p value. Maybe I want to try like p equals 1 and see what happens. See if this seems better or worse. Go ahead and run this. Whoa, this is certainly interesting. So now we get a bunch of answers that have 3 stalks. So, and I should also point out here, the values are super high, right? Like before we were seeing our values that were close to 0, if not less than 0. Now all of our values are super high. So that seems to have made things quite a bit worse. So why don't I try increasing the value of p? Maybe let's go to 5. Go ahead and run that. Somebody asked why the sum of the probabilities is not equal to 1. It should be. Just note that all of these are about 5%, right? Oh, I see. You're saying they don't sum to, like they sum to less than 1. I think the reason for that is that this is programmed. Yeah, if you look here, we're only looking at the first 10 rows. So the first 10 rows doesn't necessarily add up to 1. Okay, so let me just see if this has finished. Okay, so our p equals 5 example has finished executing. Let me go ahead and run this. Okay, interesting. So we're back to Google and Apple being our solution, which we know is wrong, but at least the correct answer is showing up here. And our values look more sensible than they did with p equals 1, right? So anyway, my point here is maybe from this, you could guess that increasing the value of p might help a little bit, but maybe p going too high is a bad thing because now we don't get our optimal solution anymore. So you can play around with this, try and discover a little bit more. You could play around, for example, with some of the parameters defined up here, right? So changing the budget, changing the risk factor, seeing what effect that has on things, changing the max number of iterations, right, in our optimizer. All of those things would likely change how consistent and how good your solutions are. All right, so I think I don't have any other things that I necessarily want to point out here. But like I said, the point of this was definitely not to have you understand every single line of code. The point here was just to kind of show what it's like for someone like me even to walk through a notebook that I haven't really seen before and try to make sense of it, right? This is not going to be a painless process for anyone. There's always going to be things you don't understand. There's always going to be things that don't make sense. But the way around that is start Googling stuff, read about it, and then start running some experiments on your own, right? And try and figure out what certain parameters do and what kinds of effects they have. All right, so I think I'll tie off the bit on going over this code here, and I'll switch over to any questions in the chat. So I know that there were a lot of people throwing stuff in the chat as I was talking. I wasn't necessarily paying attention to it. So please feel free to just copy paste your questions if I didn't get to them earlier, and I would be happy to answer them now. Will I be in the Discord server? I'm not in the Discord server currently. I don't know if I guess I could join. Yeah, maybe. I hadn't really thought about it. I kind of thought the Discord server was just for students, but maybe not. Okay, so somebody asks, could you talk a little bit about the quantum developer certificate, how to prepare for it? Unfortunately, I don't really know that much about it. I don't know what level of knowledge they expect you to be at. But what I would say is if they expect you to know, for example, a lot of what's in the Qiskit textbook, you have a good foundational knowledge now to be able to go and learn that just by reading the textbook, right? I really think that, yes, there will be some challenging parts. Yes, you will need to reread some sections to really understand it. But given what you know now, you have the tools you need to teach these things to yourself. You have all of the foundations. You have a lot of the intuition. I will just say intuition is really hard to build up, but hopefully you've been starting to get some of that throughout this course. Okay, so let's see. How can we connect with me after the course ends? So a couple of ways. Well, I think the main one would be through the Schrodinger's chat program, right? That would be one. I'll be on there a few times, I'm sure. But just staying connected with Qubit by Qubit, right? I know that we're not offering anything more advanced than this particular course, but there are going to be summer camps, and you can bet that Qubit by Qubit is going to be doing some interesting stuff in the future. So I would encourage you to stay connected through all of those different channels. I'll be sticking with Qubit by Qubit for the foreseeable future, for sure. And I know that we have some exciting stuff coming. Okay, so somebody asks about Canvas material being available after the course ends. The details of this are in an email that was sent to you and a Canvas announcement, I think, that was posted. If I recall correctly, Canvas materials are going to be taken down because we have to pay for Canvas. We pay for every user on it. And so as the course ends, we are going to be shutting down Canvas. You're free to download everything on Canvas for personal use, as long as you don't go distributing it for any other purposes. Okay, so somebody asks, I'm looking for an internship in quantum computing. Can you give me some suggestions? Yes, I actually can, because it wasn't too long ago that I was looking for jobs in quantum computing. A really good resource, this is not sponsored or anything, but this website here, Quantum Computing Report. If you haven't seen it before, it's a fantastic one. You can sign up for their emails. They give just general updates on the quantum computing industry, new quantum computers that are being released, new important papers that have been released. But if you're looking for internships, the specific one that I would go to is jobs. And then you can sort here by, different regions. If you're looking for jobs, in Europe, Asia, Australia, in US and Canada, and, got academic and nonprofit stuff. Look at these pages. There are tons of quantum computing startups out there. Like, yes, there are only a few big companies doing it, your IBM and Google and Microsoft, and you can totally apply to those for internships. I'm pretty sure they all have quantum internships. But if you don't get one of those, there are like gazillions of quantum startups out there that would be looking to hire interns. So I would highly encourage you to look into those and apply to those. And this website is like the definitive source on different quantum computing startups that are out there. All right, let's see. So, okay, a couple of people are asking me to go back to the code. Can you please explain again the set our optimization parameters code block? Yeah. I don't know that there's actually a whole lot more to explain here. Basically, what they're doing here is they're setting up some user-defined parameters, right? So this risk factor, if we increased this, we'd probably get some more volatile stocks in our ultimate selection. There's some things here I don't understand though, right? I don't really understand why this thing called penalty is equal to the number of assets. But if you wanted to look up what penalty was, we could go and find the documentation on this function, right? So I need to do a bit of investigation here to even figure out what I should Google. Let's see where we defined portfolio. If I scroll up. Okay, so it looks like, here we go. So we imported portfolio from qiskit.finance.applications.ising portfolio. So I'll just go ahead and look that up. Qiskit finance portfolio. Ising portfolio. Here we go. So this is the thing that we were using there. And boom, first one here, get operator. So I'll click on that function. Okay, this doesn't seem to give very much information, unfortunately. Get qubit op. So maybe if I go back up here, I'm not sure if it'll tell me any more about what this penalty is. One thing that I might do here, though, is, well, my screen is a little bit messed up, but I could go and sort of scroll back in this tree structure here, right? So the stuff I'm looking at right now is maybe a little bit too specific. I want to read more generally about what this penalty thing is. So maybe if I go back to Ising models, nope, that doesn't really help. Finance applications, that also doesn't really help. Okay, finance module. Okay, so maybe there's a little bit in here, some financial uncertainty problems, data providers, components. I'm not sure. So I might try and look up like a Qiskit finance overview, right? And just see if I can find, okay, perfect, here. So here's some tutorials. Because, okay, and here's portfolio optimization. So this is probably going to be similar to the thing that we've just seen. And hopefully this would start to describe perhaps a little bit about what the penalty is. Set parameter to scale the budget penalty term. I don't know. I'm not finding anything quickly. And I don't want to sit around here and waste your time too much. But this is generally the process I would try and follow, is just Google around, see if you can learn what these different things are if you don't know them. And Google should be your friend throughout this whole process. I don't know if that was necessarily what you were getting at. So please feel free to ask a follow-up question if I didn't answer what you wanted for this particular cell block. Okay, somebody sends me in a direct message. When you talked about the cost function, shouldn't 0 cost be optimal? Shouldn't the absolute value of the cost function be a good metric? It depends on which cost function you're using. So certainly some cost functions are designed so that they will minimize at 0. but some of them might have an undefined minimum, right? So for example, the cost function we're using here, it's obvious that it can indeed go below 0 because our optimal value had a negative cost, right? And so if you're minimizing a cost function that can go below 0, you don't necessarily know what your minimum is going to be. So if you tried to use absolute value here, that would not work, right? Because something that has a value of minus 0.1 is definitely better than something that has a value of 0.1. Okay, recommend a book about intro to computer science. Whew. I don't have anything off the top of my head, unfortunately. But one thing that would probably be good, like if you just want a generic introduction to computer science, I'm sure there are many online courses that do that, right? Whether it's through something like MIT OpenCourseWare or like Udemy or edX or any of those platforms could probably give a good introduction. Okay, yeah, so the person who asked about this cell block is asking some clarifying questions. I pretty much already said all of the stuff I know about this cell block at this point without Googling more. So this portfolio get operator thing, I don't really know more about that. I mean, I know from my knowledge of QAOA that we convert our cost function into an operator, right? So I'm guessing that this thing here is going to be constructing our cost function somehow. But I don't know the details of that. So I'd have to go and look it up to figure out more. Okay, good books on quantum computing and quantum mechanics. There is a great one that is referenced all the time if you want to dive into quantum computing quite a bit more deeply. It's affectionately called Mike and Ike, but it's, oh gosh, what's the actual title? I think it's Intro to Quantum Computing. Is that going to work? Book. No. Oh no, it's called like Quantum Computing and Quantum Information. Yeah, here we go. Okay. Sorry, I forgot what it was called for a bit. It's called Mike and Ike because of the authors, Michael and Isaac, Mike and Ike. Anyway, this is a legit textbook. This is like a university level textbook, so it can be hard to get through. But if you want to take the next step and start learning more details behind the math and the concepts that we taught in this course, this book goes into a lot more detail. So if you have time over the summer and want to read something interesting, I personally think the book is very well written. I think it does a good job of explaining a lot of concepts, but it is university level, so it is challenging. I would offer that as a warning, but not necessarily to scare you off. I think you can totally handle it. All right. Let's see. Thank you for everyone offering warm wishes. So somebody asks, how should we approach some of the functions that we don't understand in this notebook? So I'm gonna go out on a limb here and say that there probably aren't any courses out there outside of maybe some universities, but there probably aren't any courses out there that are specifically going to teach you, finance and quantum computing, right? Quantum computing is so new that something as niche as like quantum finance or, quantum machine learning, there might be some courses out there, but it's going to be generally pretty hard to find. And that's why we, like as a teaching staff, we felt it was important to walk through an example like this where you kind of just explore and teach yourself, because due to the lack of resources for quantum computing online, a lot of your learning is going to have to be like this, just kind of out of necessity, right? I wouldn't be surprised if there were no good courses out there for quantum finance. And so instead, you have to learn this kind of stuff just by playing around, Googling, reading tutorials, reading docs, changing the code, running it, and just trying to teach yourself. That's because quantum computing is so niche, that is the way that you have to learn a lot of the time. There might be a course for quantum finance. I don't know, haven't tried to look it up. But generally speaking, if you keep going with quantum computing, you will come across a lot of topics for which there is no formal instruction readily available. And so you have to just end up teaching yourself. Yeah, so for all of you asking, how do you design a cost function? How does this cost function work? Like I said, I think this would be the place to look for it. But I didn't really have too much success finding, well, I guess maybe this is the cost function it's using, perhaps, and then you could read a little bit more about what exactly each of these things means. I'm not exactly sure. It seemed not super easy to find the documentation as I was just Googling now. But I would be surprised if there was literally no documentation out there. It does probably exist. Okay, yeah, so people are offering some suggestions in the chat. Looks like there are a few courses. Oh, that's just regular machine learning, I think. But yeah, there might be courses out there for some quantum topics. Just a general warning that at this point in time, there might be some things where you gotta just teach it to yourself. And oftentimes, yes, that is harder than just taking a course on it because you have to kind of struggle and figure things out on your own. But I also think that's a good skill to have, right? Because you're not always going to have teachers and instructors there to guide you through things. Once you start getting to more advanced topics, the only people who are going to teach you are papers and researchers and people who write code. And so that's the language you have to start speaking. Okay, cool. All right. Hey, I think they have heard us loud and clear for requesting a sequel, something that's a more advanced version of this course. Like I said, it probably won't happen last year, but you never know. I would say keep following Qubit by Qubit because the team is only growing. We're only offering more stuff, and you never know what's going to come in the future. I am personally really excited. So, all right. Well, I think I'm going to wrap things up here then. As always, I hope you had a great time. I hope you really enjoyed the course. I guess this is it, which makes me a little bit sad too. But best of luck with all of your futures in quantum computing or STEM or whatever you choose to pursue. I hope that you have more confidence in yourself and yeah, just more interest in this field. Because I think, as you've seen from me, I find this fascinating. So good luck, have fun, and yeah, maybe we'll see each other around sometime in the future. Bye.